Okay, so what we'll cover now is how to make assemblies which look like castings, because unfortunately not everything in the world can be made on the water jet, and if you start dealing with three-dimensional structures which have to be very rigid, heavy, and machinable, you have to make them from solid, and the two choices are always to mill it out from a solid block, which is expensive both in terms of material and machine time, or mill it out from or machine a near net shape. Near net shape could be a casting, a forging, or something bent and then machined. So obviously there's a huge advantage of a near net shape, and most of the big machinery in the world is made from castings. For that reason, in a R&D environment, castings are a tedious process because you have to make patterns. It's not the kind of thing you can easily do at home. So there is an alternate process which is to build it up from segments by brazing. Now the other process which is used a lot in industry is weldment. It's just to build it up by welding. But to build up by welding needs a lot more skills than to build up by brazing. Because there are two disadvantages to welding. First, there is heavy distortion, no matter how carefully you weld, because of the shrinkage of the weld bead. There's always distortion. But the other disadvantage of welding, besides needing skills, is that you cannot weld together very dissimilar metals. Sometimes, in same problem in a casting, sometimes you would like to have one side of the machine made of steel, but the other side made of brass, because you want to do some bearings or machinings there. Now you can't have a casting which one end is steel, one end is brass. It's also, you can't have a weldment like that, because you can have two types of steel welded together, but not steel and brass. But when you build it up by brazing, you can make each segment from a different material according to the best material you need. So just to illustrate it, we'll just make up some imaginary part that we want this to be steel, but we want a boss made of brass here, and later on it'll get machined on the critical points, because it's a near net shape. So all the parts are cut out on water jet, and usually you have to cut out some tab to register it, and here I didn't bother to this. As you recall before, we usually cut out a little finger, a little square hole, so everything is registered when you put it together. We didn't bother here. Another way you can do is you can tack things in place, okay? And I usually do it with a laser welder, which is a little bit exotic, but you can just put a dowel pin or anything. So let's just tack it in place with a laser welder, and then we'll prepare it for brazing. But the laser welder is really luxury here. You don't have to do it. You can also spot weld it, tack it with a spot welder, but not the brass, and so on. Okay, so let's just tack things in place where we want them, and then we'll prepare. Okay, so these laser welders, which are about $20,000, are surprisingly versatile machines, and if your budget allows it, I highly recommend them, because the advantage of them over any other welder that they can weld into very hard to reach places. As long as you can see the place with a microscope, it will weld there, just the light has to get there. And they can weld dissimilar metals together, because the pulse is so fast that nothing has a chance to cause trouble or to oxidize. So they actually weld without any inert atmosphere, because the weld is so fast that even regular steel doesn't oxidize. So let's just tack things in place. Okay. So that's welded. It's also a bit crooked. These are temporary welds. I can break them if I want to, but that's good enough. Okay, and I want a brass boss at this place. Good. So that's the beauty of the laser welder, that it doesn't care what the metal is. I can weld aluminum to steel, silver to lead, and I can weld anything to anything. So the brazing is done by placing little pieces of brazing wire, which is typically a silver, copper, alloy, some other materials, and flux. And the flux is what makes it wet, the metal, because the flux dissolves the oxide, and the flux protects the metal from oxidization. So without flux it wouldn't work. Now typically there is a white flux, which is basically borax, which is the most common flux for all non-ferrous and can be used on iron as well. And there is a black flux, which actually, I'm not sure about the composition, I think it's some fluoride salt, which is used for stainless and harder to braze materials because it's more aggressive. Okay? The only expensive part here is a wire. The fluxes are there cheap. So the way you deal with this is, okay, let's say we can use a white flux on the brass, although it's not going to make much difference. Which flux? So if you want to do a very nice job, it's nice to put a wire all around it. It can be done, although the material will flow, but to be really sure, you can put it all around it. And what I can do here, the flux is like a paste. I can just fill the corners, wipe off the excess, and place a piece of wire on it. And wash my hands well, because I don't know how corrosive that is. So you just put in a bit of flux everywhere. Too much flux is not a big problem. It just cleans up easily later. So you're basically creating a little fillet with a flux where you want the braze fillet to be. And we'll try the white flux on the brass piece, although it's going to work with other flux as well. And just wipe away the excess flux. And the reason I'm doing it, that the flux somewhat attacks the metal. So just for cosmetic reasons, I don't want surface defects on the metal. Because at a high temperature, the flux will actually interact with the metal and slightly attack it. Just lay little pieces at the corners. In theory, if there is good wetting, one piece will run everywhere. But since I don't know how well the parts fit, and I also would like to have a fillet, so I'm actually putting plenty of material to create a nice fillet. Now obviously when the material starts melting, if it was a vertical wall, the wire wouldn't really wet, it just fall off. So if you try to lay out everything that's at a horizontal plane. But if you have no choice, if you had to weld something like this and something like this, or braze, and you wanted a joint here. So there's a few tricks you can do. You can put a lot more stuff on top, hoping it will be pulled down. Or another trick you can do, you can drill a hole here and put inside a few slugs of brazing wire with flux. So as it melts, it will come out and fill the gap. The last choice is to braze it in 2 steps. So first do all the horizontal walls and put it on the side, do the other direction. But to do that, these have to be secured with welds or pins, so when you turn it around, they don't fall off when the braze melts. So since this is laser welded, if I had a vertical braze, I could have put it on the side and done a second braze. It's problematic because when you do the first braze, it gets oxidized. Okay, so you have to fill it with flux, even if it wouldn't braze. On the first braze, the gaps have to be filled with flux so they don't oxidize. So it is better, if you had to do brazes on 2 planes, it's better actually to figure out a way to do it all in one braze. Now the gaps can be anywhere from 0 to maybe half a millimeter, because if the gaps are too big, the capillary reaction will be too weak. So you can buy different wires with different abilities to fill gaps, but in general, if the gap is more than half a millimeter, it's not a good idea. You should be machined tighter. You can also get those in foil. So sometimes you have 2 big areas, so you can put a foil underneath covered with flux. Okay? And for good measure, I will just add a bit more flux. Basically, the wire has to be half buried in the flux. Okay, the next step, we put it in the oven. Typically, we set the temperature for about 750 C. The temperature has to be about 100 degrees above the melting point of the braze alloy, because you want, A, you want to be sure it melts, and B, it has to be very liquid. You want it to flow beautifully. But if it's too high, it just causes needless oxidation. So you look up the melting point of the alloy and add anywhere from 50 to 100 degrees. So this is, I believe, melts at about 680 C. So I'm setting it for 750 C. Okay, and then you just come back in an hour and it's all done. Now, if the piece is big, the recipe for brazing is the same recipe as for making a turkey. So it has to reach temperature, and then you give it about 1 hour for every kilo extra. So it's because it takes time for the body to absorb heat and equalize. So since this was maybe half a kilo, I just has to get to temperature and then maybe another half an hour. Okay, so now this set, once it reached temperature, it's set for at least half an hour more, which is enough to equalize the temperature. So we turn off the oven and we don't touch anything until it cools down to about 500 degrees, and we can touch it. Okay, so this is the part we took out from the oven before, after it cooled down, and we sandblasted it. And you can see a few things. First, you can see that you have a casting, which each part is a different metal, which is very useful. For example, you could have stainless steel inserts and anything you want, hardened inserts, all in the same casting. Second thing you can see is a nice wetting, so that it made a nice fillet. And if you wanted to paint it and you wanted it to really look perfect, all that you have to do is just sand the fillets a little bit to round them up. So all that you'll have to do is take something like this, bend it over, and just go like this, a bit more than that, until the fillet is smooth. Okay, and this way, once you paint it, it looks like a perfect casting. It looks much nicer than a casting, because a casting wouldn't have such nice, smooth surfaces. Now, it is as strong as a casting. It's actually a bit stronger, because casting is made from cast iron, and cast iron is much weaker than steel. So as a comparison, for example, this is a piece of cast iron, and if I put it in the vise, I should have no problem breaking it, and certainly if I hit it with a hammer it will shatter, because cast iron is so basically, as you can see, and this is very high quality cast iron. The reason I know that, it's out of a very old machine, and the older the better the cast iron was. But basically cast iron is not such a strong material. As you can see, you can break it by hand. Just hit it with a hammer, it's broken. That's why cast machinery is so heavy, because the material is actually not strong. On the other hand, if I take the casting built up by brazing, and I do the same test, so here I should be able to bend the metal without actually breaking the joint. So let's put on a big wrench on it. Go from here. Like this. So you can see that it's much stronger than casting, both for regular stress and also for hammering. So altogether it looks nicer and it's much stronger and more versatile.